Degree of freedom, or DOF, is related to the motion possibilities of rigid bodies. Kinematic definition for degree of freedom of any system or its components would be the number of independent variables or coordinates required to ascertain the position of the system or its components. Let's understand degree of freedom in more simpler terms. Let's take the example of a car. A car is moving along a straight road. Now, how to determine if it has traveled from one point to another? It's simply done by calculating the distance it has traveled. So, distance here is the independent variable. Since only one independent variable is defining the motion of the car, hence the car has degree of freedom 1. Now let's take another example. Here is a windmill. The rotation that the windmill makes is dependent upon the independent variable theta or angular displacement. Since there is only one independent variable, the degree of freedom of windmill will also be 1. Now let's take the example of an aeroplane. The plane can move up and down in the air or in the Cartesian coordinate system. Up and down the y-axis, that is plus y and minus y. Forward and backward, that means towards plus x and minus x axis, and also towards us and away from us, or plus z and minus z axis. It can also rotate about all the three axes. Let's say theta is the angular rotation about x-axis, phi is the angular rotation about y-axis, and gamma is the angular rotation about z-axis. So altogether, there are 3 translation motion and 3 linear motion about the x, y and z axis respectively. So the 3 translation motion has 3 independent variable x, y and z, whereas the 3 rotational motion has 3 independent variables theta, phi and gamma. Now, the degree of freedom of a robot typically refers to the number of movable joints of a robot. A robot with 3 movable joints will have 3 axes and 3 degree of freedom. A 4-axis robot will have 4 movable joints and 4 axes, and so on. While it is not absolutely the case, most pick-and-place devices and robots have several capabilities like moving in a straight line, moving object from one place to another, and many more. But the most amazing movement would be of roll, pitch and yaw. Let's take the same example of an aeroplane to understand roll, pitch and yaw. An aircraft in flight is free to rotate in 3 dimensions, in which yaw means plane's nose left or right about an axis is running up and down. Pitch means plane's nose is running up or down about an axis, running from wing to wing. And roll means plane's rotation about an axis running from nose to tail. Similar is the case with robots. The x-axis is considered to be the machine's forward direction. Rotation about the x-axis is called roll. Rotation about the y-axis in case of robot is called pitch, and the rotation about the z-axis is called yaw. Now let's understand some of the common pick-and-place robots. First is a one-axis robot. It can pick up an object and move it along a straight line. The two-axis robot can pick up an object, lift it, move it horizontally and vertically, and set it down or present it on XY plane without changing the object's orientation. The three-axis robot can pick up an object, lift it, move it horizontally and vertically, and set it down or present it anywhere in the X, Y, Z space within reach of the robot, and it also doesn't change the object's orientation. The four-axis robot can pick up an object, lift it, move it horizontally, and can set it down or present it in the XYZ space. But in case of four-axis robot, a change of object's orientation can be seen along one axis, so it would be an example of yaw. The five-axis robot can pick up an object, lift it, move it horizontally, and set it down in an XYZ space, while changing the object's orientation along two axes. That means this is an example of yaw and pitch. A six-axis robot can pick up an object, lift it, move it horizontally, and set it down in an XYZ space, while changing the object's orientation along three axes. So this kind of six-axis pick and place robot has all the three movements: yaw, pitch, and roll. The seven-axis has all the movements capability of a six-axis robot, along with the ability to physically move the robot from one place to another in a linear direction. It is performed typically in a horizontal motion along a rail. All the examples that you have understood are of simple pick and place kind of robots and devices. In order to understand how complex robotic configuration works, we need to dig deep into 6 degree of freedom robots. This we will discuss in the next lecture. A typical robot requires 6 degrees of freedoms in 3D space. The first 3 joints helps in reach, and the other 3 joints are in the wrist for orientation. However, the configuration is based upon first 3 joints only, that is, for the joints helping in the reach of the robot. Now, as per the robotic configuration is concerned, corresponding to the reach or the first 3 joints in the robot, we have 4 basic configuration. First is rectangular or Cartesian, second is cylindrical, third is articulated, and fourth is spherical or polar. Let's understand them one by one. First we have rectangular or Cartesian configuration. In this system, there are 3 basic movements along 3 rectangular axes. These motions are provided by rectangular box type sliding joints. The vertical motion is provided by the joint on the vertical column of the robot's base. The 2 horizontal motions are provided by the joints on the horizontal arms, in which one is mounted on the column and another is on the arm. This configuration is suited for straight line movements and side-to-side movements. These robots are used for pick and place operation, as in material handling, machine loading, etc. Second, we have cylindrical configuration. Here, there is 1 rotary and 2 linear motion of the robot. The rotational motion in this type of configuration is provided by rotary joints between the base and the column. The vertical movement is provided by the linear joint between the column and the horizontal arm. Now, the horizontal motion is because of the sliding joint in the arm. The motion envelope of the end point is cylindrical. This type of configuration is suited for motions around fixed base as in assembly operation, material loading, or machine tool table. This kind of configuration is also utilized for spot welding. Third, we have polar or spherical type of configuration. Here, we have two rotary motion and one linear motion of the robot. There is a rotation between the base and the column, and also between column and the arm. The linear motion is given by the sliding joint on the arm. This kind of configuration is used in spot welding, gas welding, arc welding, and machine loading operations. And last but not the least, we have articulated or revolute type of configuration. Here we have three revolute joints or three rotary motion. This configuration is also called anthropomorphic or joined arm, and it resembles a human arm. The base revolves around the vertical axis. The base and arm, that is the shoulder, and another arm, that is the elbow, have rotary joints. This type of configuration is used for spray painting, arc welding, gas welding, material handling in die casting machine, and many more. Some robots are also there which contains a mix of different configurations like gantry robot, SCARA robot, Delta robots, and collaborative robots. They have huge impact in many sectors as per time, cost of production, and efficiency is concerned. I call them the white collar robots. Here, let's first understand about gantry robots. A gantry robot consists of a manipulator mounted onto an overhead system that allows movement across a horizontal plane. They are usually large systems that perform pick and place applications, but they can also be used in welding and other applications. Gantry robot systems provide the advantage of large work areas and better positioning accuracy. Position accuracy is the ability of the robot to place a part correctly. These gantry robots are easier to program with respect to motion because they work with the XYZ coordinate system. Another advantage is that they are less limited by floor space constraints. Next, we have SCARA robots. SCARA is an acronym that stands for Selective Compliance Assembly Robot Arm or Selective Compliance Articulated Robot Arm. SCARA robots function on three axes, that is X, Y, and Z, and have a rotary motion as well. SCARA robots excel in lateral movements and are commonly faster moving and have easier integration than Cartesian robots. Typically, SCARA robots are used for assembly and palletizing. They are also sometimes used in biomed applications. And then we have Delta robots. Delta robots are also known as parallel robots. They possess three arms connected to a single base, which is mounted above the workspace. Delta robots work in a dome shape and can move both delicately and precisely at high speeds due to each joint of the end effector being tightly controlled by all three arms. Delta robots are often used for fast pick and place applications in the food, pharmaceutical, and electronic industries. The last white-collar robot in my list is collaborative robot. Collaborative robots or cobots are robots that can directly and safely interact with humans in a shared workspace. Cobots are typically used for pick and place, palletizing, quality inspection, and machine tending.